This is sodium number 11 here on the uh, left-hand side of the screen. And then we have chlorine over here on the right-hand side, but not in this last column. Okay. I went over this on Monday, I think, very briefly. May have said this really fast, and I may not have said to all classes, but this right here, these 8 elements, or these not 8, there's 7, but they're in column 8. If you count, we only count these tall columns. This is column 1, column 2, and then jump over here 3, 4, 5, 6, 7, and 8. And on some periodic tables, you'll see Roman numerals above these. Okay. And that's what they'll be. They'll have those Roman numerals, and they usually have the Roman numeral A with it. So 1A, 2A, 3A, 4A, 5A, 6A, 7A, 7A, and 8A. Then these down here in this valley, okay, the valley between the two mountains, right? These would be labeled also 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 in Roman numerals, and they have B following their Roman numeral. That's usually how it's split. Now, there is a different way to split the A's and the B's, and you'll see that on periodic table charts for engineering. Okay, all right. There's like two ways scientists look at these. So we're going to use the one with the mountains being A and the valley being B. Okay, for this class. Not that we talk about that a whole lot, but that's just what we're going to do. So this 8A over here, these are called noble gases. And the reason they're called noble gases is because in their outermost shell, they have 8 electrons. And at 8 electrons, you are full. Okay, the outermost shell cannot take any more electrons. So these are very stable. I was talking about some elements being stable and some elements not being stable. Well, that's radioactive decay, but also there's a stability of uh, how much they want to interact with other things. Okay. And because their outer shell is full, they don't need, okay, to interact with anything else. So they're very happy with themselves. Okay. Talk about self-confidence and happiness. They're aloof too, because they don't need anybody else. They don't need anything else. They're aloof. Okay. They don't interact with anything else on this table. So those early chemists, they noted that they never saw these things interacting. They didn't see these elements, the ones they knew about, which they didn't know about all of them, but they never saw them interacting with other things. They were always off by themselves. They were very pure because of that too. Okay, they they were always just themselves. So they gave these the name of noble gases because they were kind of like the nobility. All right, they stayed aloof. They didn't mix with the peasants. They kept off to themselves and just very at least on the outward appearance, very happy, right? Okay, had everything they needed, didn't need anything else. Well, everything on this table, let's stick with that nobility aristocracy analogy because it kind of works. All right, everything else on this table would like to be like the aristocracy. Everything else on this table would like to have that full outer shell. They like to at least have that outer appearance of being a nobility, even if they aren't. They're not going to change their identity because they're not going to change their proton number, but they'd like to change that electron number. So chlorine over here would really like to just gain an electron. If it could just get one more electron, it's got 7 in its outer shell. And if it could get one more, then it would be like argon. Okay, it would be full in its outer shell and have this outward appearance of being noble. Okay, it can't do that because in order to attract another electron to it, it has to have another proton. Okay, positive and negatives. It takes a positive to attract another negative. Sodium over here, it's in column 1, and these column numbers actually tell you how many electrons are in the outer shell of the electron, or of the atom, sorry. So everything in this column has 1 electron in its outer shell. Everything here in column 2 has 2 electrons. Jump over here, and in column 3A, we've got 3 electrons, 4 electrons, 5 electrons, 6 electrons, 7 electrons, 8 electrons. So that's how the table helps you tell about that. This table tells you all sorts of things about these electrons just by looking at it, if you know what the arrangement means. And this is not a chemistry class, so we won't get into all of that. But just to understand bonding here a little bit, sodium would like to get rid of that 1. That one lone electron, it's dead out in its outermost shell. If it could get rid of it, it would have the outward appearance here of neon then. Okay, that would be great. But as soon as it gets rid of an electron, it has 11 protons in its nucleus, and it's going to pull another electron to it because electrons are energy particles and they're out there floating around. Okay, given off, they're released, and they're captured all the time. So, have a problem. This one can't attract the one it wants, and this one can't get rid of the one it wants to get rid of. But to personify these and make them like people, right? Okay, if chlorine and sodium were to meet up and say, hey, sodium say to chlorine, hey, I have got this electron. I would love to get rid of it. And chlorine's like, oh, I would just love to have it. Okay. Sodium says, take it. I don't ever want to see it again. And chlorine's like, that's fine. I'll take it. I don't ever want to get rid of it. They can do that. But if chlorine and sodium get too far away from each other, chlorine is going to lose that extra electron because it can't hold on to it. And sodium is going to attract another unwanted electron back to it. Maybe the same one, maybe not. Okay. But they're going to wind up right back where they started. So they have to stay close to each other in order for chlorine to keep the use of that electron all the time and for sodium to not have to grab another one. And that closeness, that relationship there of chlorine taking that electron and keeping it and sodium being able to, ignore it and get rid of it, forms a bond. And that's the ionic bond because it's formed from this giving away and taking. So giving and taking of one or more electrons. You don't have to have just one in this. Okay, these over here in column 2, they can get rid of 2 electrons, and they can share with the same, like they can share with anything in this column 6 here. Like oxygen would love to get 2 more electrons. So magnesium likes to get rid of 2, and magnesium and oxygen like to form a compound called magnesium oxide. Okay, so that's sharing of 2. But magnesium can also give one of its electrons to chlorine, to one chlorine atom, and another electron to a different chlorine. And so it's sharing with 2 different chlorines, and that forms magnesium chloride, which is a salt, and it's one of the salts you find in Epsom salts. Okay, so these are examples of ionic bonds. Okay, questions on ionic bonding? Does that kind of give you an idea of what's going on? So it's a give and take relationship. Okay, one's giving, the other one's taking. So the next we're going to talk about then is covalent bonding. And covalent is sharing. Okay, they're sharing electrons. Okay, so covalent atoms share one pair of electrons. So the diagram here, that's the ionic bond I just showed you, and kind of another explanation of it. So let's look over here at covalent bonds. The example they're going to use is hydrogen. And hydrogen is a little bit of kind of a different animal. If you look where it's at on that periodic table, it's up here all by itself on column 1. It has 1 electron, but so it would like to gain an electron to be like helium. So a lot of times it acts like it belongs in this column, but if you notice, it's a different color. Okay. So it has some different properties, and that makes it do some kind of unusual things, okay, that you wouldn't necessarily expect of things in this column. So part of the time it can behave like it belongs there, and part of the time it can do other things. So anyway, it's put there. It can form covalent bonds and often does. That's its excuse me, its most common type of bond to form. Okay, even though you'd expect things in that first column to form ionic, this one doesn't. It's mostly covalent. And so it's going to share. And hydrogen, like I said, hydrogen is one of those that likes to bond to itself. Hydrogen gas is always two atoms of hydrogen bonded to each other. Okay. Oxygen, and some others are always going to form, they're called diatomics. Okay. So this is what it does. One electron will, and then the other, okay, this atom has an electron and this atom has an electron, and what they do is they will share. So this is a schematic here kind of showing what that might look like. And so if you can kind of see how this goes, the electron here will orbit its original atom. This one here is going to orbit its original atom, but the orbits overlap. Okay, they get close enough together that their orbits overlap to where at any given time, this hydrogen feels like it's got 2 electrons. And at any given time, this hydrogen feels like it also has 2 electrons, has the use of those electrons. Okay, so this is sharing, and we refer to that as covalent bonding. Okay, so question, have to unmute yourself to answer. Which one do you think is the strongest? When we look at chemical strength, which of these bonds are the hardest to break apart if we want to get those atoms out separated from each other again? Which one would you think would be the strongest or the hardest to break? Okay, why do you think that way? Okay, why do you think covalent or why do you think ionic? Okay. Um, and when we start talking about some other bonds, there's some other bond types, and really only going to talk about one other bond type. Actually, they're both the two strongest of the bonding types, really. Okay, but covalent is stronger. Okay, covalent is the stronger one. And to help students remember that on the test, I go back to the people analogy. Okay, and let's look at it as if it were a relationship. All right, you've got sodium and chloride, and one is doing all the taking and one's doing all the giving. Okay, sodium's, let's go back to the periodic table here. Let me can okay, so sodium is giving away its electron, and chlorine is doing all the taking, and that's okay. I mean, that's kind of what they want, right? That's why they're in this relationship to start with. But if when it comes to positive pull, positive attractions, and all of that, magnesium's got a stronger positive pull than sodium. It's a more attractive element. Okay, all right. Think about it that way. It's a more attractive element. So sodium and chlorine are fine if they're walking down the street one day, right? No problems. But magnesium comes along, and magnesium wants 2 chlorines, right? It needs 2 chlorines to bond to it. So it's looking for chlorines, and it walks by, and chlorine, is like, whoa, by sodium. Okay, and that happens. Okay, it's an element with a slightly stronger, or even more, not just slightly, but can be kind of a heavier or a stronger positive charge, can strip an element out of a compound like that. Okay, we do it all the time in chemistry. You've got a beaker of one compound, and you stick another element in there, and it'll pull, like say chlorine. It'll pull the chlorine off the original cation is the term, okay, and form a new compound. Okay, so if I had a beaker of sodium chloride and I add a bunch of magnesium in there, I'm going to wind up with magnesium chloride and sodium off by itself. Okay, all right, it's called a single displacement reaction, and you don't necessarily need that for this class, but that's what happens. Okay, so and it doesn't require any energy. I do not have to heat that solution. I don't even really have to stir that solution. Usually I'm going to, because I'm impatient and I want this reaction to hurry up and happen so I can then filter it out and get what I want out of it. Okay, the reason I did it. But I don't have to. I can just let it sit there, and over time, they're all going to, because they move, okay, they bounce off each other. They're basically all going to eventually uh, do the reaction, okay? And so, no energy. However, to go up here and split these 2 hydrogens apart from each other, it's going to require a massive amount of energy. Okay. So usually it's going to be heat. In this case, usually they do that with electricity. Okay, run electricity through there to split it. We're not splitting the atom. We're just splitting two atoms apart. Okay, the hydrogen bomb was splitting a single atom. Okay, we're just trying to get these two atoms into their single form because they're not normally that way. Okay, oxygen, same way. I talked about the ones that are diatomic. Hydrogen, oxygen, fluorine, chlorine, bromine, iodine. These 1, 2, 3, 4, 5, 6. Oh, nitrogen starts here. Nitrogen. Okay, there's 7 of them that form kind of a. Well, here they form a 7. This forms a 7 if you look at it that way. And then you got to remember the hydrogen's part of that group as well. Okay, um, and there's 7 total diatomics. I don't quiz you over that, but it's something that's a useful piece of information to know if you go into chemistry later, that these are always found in their gaseous form as 2 atoms bonded to each other. Okay, O2 into H2, Cl2, okay, chlorine gas. Okay, all right, so questions over covalent bonding, differences between the two, ionic and covalent? Nope, good, okay. So a third type of bonding that becomes very important in our organic molecules that we find inside the cell is what's called hydrogen bonding. And of course, we have to have the other 2 types of bondings going on to form the molecule itself. But what we find with hydrogen bonds is that these are bonds that help hold um, multiple molecules together in a structure, or like in the case of the DNA, which I'll say this again when we talk about nucleic acids in particular, but DNA has that spiral double helix. What maintains that shape are these hydrogen bonds. Okay, what causes it to curl into that shape is attractions between hydrogen and oxygen or nitrogens. In the DNA, it's the hydrogens and oxygens, or hydrogens and nitrogens in another part of the same molecule that causes it to twist. The example here is using water. So water is 2 hydrogens bonded to an oxygen. These are covalent bonds here going on. So that means that you've got these overlapping orbitals, and generally speaking, the shared electrons spend more time here in between the 2 or the 3 atoms. Okay, but in between the 2, if you're looking at each of the 2 bonds separately, uh, than outside. And what that does is that winds up giving oxygen this overall negative feel if you approach it from this side, and hydrogen will have an overall positive feel if you approach it from this side, because you've got, they both have their extras. Okay, and then this one's, or they're missing them, they're pulled inside. So what you're going to feel here is that one proton that they've got, and not so much the electron, because it's being shared more inside, spending more time inside here than rotating around out here. Okay, and so this is kind of like a magnet, if you want to think of it that way. It's got a pole here, it's negative, and it's got a pole on this side that's positive. And so magnets attract each other, right? Opposite ends, though, positive to negative ends. So the negative portion of the water molecule is going to be attracted to a positive portion of another water molecule. And since we've got several spaces here, okay, and 2 positives on the side, really, you can get these attractions, multiple attractions between the same atom and many other atoms. Okay, this is something that gives properties to water that are very unique to water. Water likes to attract to itself. It will bead up on a like wax surface. Okay, part of that's because wax is a lipid, and it doesn't like water, and water doesn't like it, so they repel each other. But water attracts to itself. Okay, if water didn't attract to itself, it wouldn't bead up, it would just not mix with the wax. Okay, but because it doesn't mix with the wax and attracts to itself, then you get this beading. Okay, beading up into a little droplet. And Another thing that if I were in the lab today, I'd be showing you is the meniscus in the graduated cylinder. Most of you've seen that before too. But when you pour water into graduated cylinder, the water will have a little bowl, okay, inside. It's not just flat across between the lines, and you have to read from the bottom of that little dip. What causes that is the water's attraction to the side of the glass. Okay, glass is made up of molecules, and so you have this type of bonding going on between the water and molecules in the glass, and it causes it to kind of creep up the side, so to speak, just a little bit. Capillary action, capillary tube, that water will climb up even higher. You can kind of do this at a restaurant or at home if you have straws. If you get a clear straw, you can take a straw and you can stick it into water. You can stick it into any beverage, but uh, the higher the water concentration, the more effect you're going to get on that. So pure water would be the better thing to see it with. You can stick that straw into water, and you can see that the water in the straw will go up just a little bit higher than the level of the water in the glass. Um, that's because of this pulling up the sides, attracting to the molecules of the straw. Okay. The smaller the diameter of the straw, the higher up that water can pull itself by this attraction, just kind of climbing up the sides. By attracting to the side of the straw and then attracting to the water behind it, pulls the water up behind it. Okay, it pulls its friend up too. Okay. Sometimes I think a way to envision that is like the game Barrel Full of Monkeys. It's kind of hook on each other and keep climbing. Um, so a capillary tube is very, very small. The diameter inside is tiny. It's really, really narrow. So you can get like, an inch or two of water column forming up that thing above above the level, sorry, of the water in the container that you stick it into. Okay. So that's one of the properties of water that's caused by hydrogen bonding is its ability to adhere to other surfaces that it can attract to, wax not being one of those, okay, and attract to itself. And adhere, that's adhesion to something else, cohesion to itself. And later on, we'll talk a little bit more about water in the cell, and those terms and these ideas will come back into play. Okay, so again, why I'm having to lay this foundation now is because later we're going to talk about things where I'll be referring back to this stuff. So chemical reactions are just the making and breaking of bonds between atoms. Okay. And as I've said before, that's life. That's life. Life is nothing but the making and breaking of bonds. Our physical being is just made up of the making and breaking of these chemical bonds. And when these bonds are made and when these bonds are broken is controlled by proteins. And those proteins are coded for in the DNA. The DNA doesn't code for anything else. It just codes for proteins that govern and regulate the making and breaking of chemical bonds in our body. Okay. So it's all about proteins in the end, amino acids and proteins, and the chemical reactions they control. A change in chemical energy occurs during a chemical reaction. Um, we have some terms for that. Endergonic absorbs energy, and exergonic releases energy. Uh, you may have had some different terms that you learned. They're very similar. Uh, because the easiest way to teach this to students is to talk about heat as the form of energy. So you probably have endothermic and exothermic as the two that you learned in school. Does that sound familiar to some of you? Right? Okay, so endothermic is the same as endergonic. Okay, endothermic, the heat went kind of basically into the reaction. It absorbed that heat energy to make the reaction happen, and it made everything around feel cold. So if you were holding the test tube when it happened, then your hand got cold. Okay, they've kind of stopped doing that because on the heat side, some uh, people actually mix too much and they burn themselves holding the glass because it got too hot. Okay, so those are kind of like not recommended reactions anymore. But if you have seen a first aid kit where they have those instant cold packs, what that has is that has little ampules okay, inside little glass ampules that hold one chemical, and outside is another chemical. And you mash that to break those little ampules. Those two chemicals mix, two substances mix, and that is going to be an endergonic reaction, or in this case, also specifically an endothermic. That is a special type of endergonic reaction. Endothermic is going to pull energy in from outside to make that reaction happen, and that lowers the temperature, creating the ice pack. Okay, creating that cold. Okay, so that's an example too where you may have seen that if you hadn't seen it in science class. Um, Exergonic is the same basically as exothermic. It's just this is more, these two terms here are more inclusive. They include energy types other than heat. Okay. Endothermic, exothermic refer specifically to heat. Okay. Not every reaction, involves heat energy. There are other types of energy, have light energy, things like that. So exothermic releases the energy out, so that's one where you would feel it get hot. So if you've ever bought any of the little hand warmers, it's like the same philosophy of the cold pack. You've got two substances, the little ampules inside, you mash it, that breaks the little ampules open, mixing the two substances. This one, however, is exothermic, so it's going to give off energy, release energy out to the environment, so the little warmer gets warm and your hands do too. Okay, chemistry in action. Okay, that's something you've probably used and not even thought about it.